we are going to go ahead and perform a calculation of stoichiometry using the gas law. Okay, stoichiometry and the gas laws. So let's go ahead and look at our problem. And what we have here is we have the decomposition of ammonium nitrate. And it is solid, and it's decomposing into N2 gas and H2O gas. The N2 gas, so we're given information on the N2 gas, the nitrogen. Gas was collected at a pressure of 1.2 atmospheres, a volume of 15.92 liters, and a temperature of 25 degrees C. Part A is how much of that gas was collected, how many moles of the gas was collected, and then how many grams of the ammonium nitrate of that reactant were required to decompose and generate that amount of nitrogen. So we have a stoichiometric problem, and the product in this case is a gas. All right, let's go ahead and kind of write. What I do is I typically write down our reaction and write down the information that we're provided. So we have ammonium nitrate decomposing to a nitrogen gas and water. And what we're provided information on is the nitrogen gas that's generated. And I write down the information of reactants and products that's involved in the question. So we have a pressure here. We're going to collect the N2. We have a pressure of 1.2 atmospheres at a volume of 15.92 liters and at a temperature of 25 degrees C. So what we're asked in part A is how many moles of nitrogen produced, and then based on the moles of nitrogen produced, how many grams of the ammonium nitrate is required to produce that amount of nitrogen. So this is like any stoichiometric problem. And when it comes to stoichiometric problems, we always, regardless of what the state is of the reactant or product, be it a solid or a gas or even aqueous, we have to go through the molar ratio, which is entity-based. So regardless, again, whether it's solid, whatever the state is, always, in our case, what I identify as calling build the box, identify the moles of what we're given, the moles of what we're asked about, and then in this case, convert that into relative grams. So nitrogen is a gas, and so when it comes to determining its moles, gas law, PV equals nRT. And from that, we're going to identify N, which is the moles of nitrogen. Okay, so let's do that, and we can come back to here and then complete this. Let's do part A, which is the identification of the moles of gas, of nitrogen. So we have PV equals nRT. And in our case, what we want to solve the moles of N2. So the moles of N2 equals PV divided by RT. And we're going to plug in our values. What we want to be careful is all the values that we use are in the correct unit system, and what by and large dictates our unit system is the value of the R constant. The R constant, being a constant, equals 0.0821 atmospheres, liters, moles, Kelvin. So all the other terms, before we go ahead and perform the calculation, have to be in these units. So the pressure, we need to make sure that the pressure is in atmospheres, and the volume is in liters, moles, and the temperature is in Kelvin. So let's go ahead. We're going to say N, the moles of nitrogen. The pressure was in atmospheres, so we can go ahead and use the 1.2. Now what's always nice is to write down the units and then track at the end the unit cancellation to be sure that we performed everything in the correct units. The volume must be in liters, and it was given to us in liters at 15.92 liters, divided by our R constant, 0.0821, atmospheres, liters, moles, Kelvin, and our temperature has to be in Kelvin. Now, our temperature was not given to us in Kelvin. Our temperature was given to us at 25 degrees C. To get that into Kelvin before we can use it, we are going to add 273 to it. So our temperature value will equal 298 K. And now we can go ahead 298 K, and now we can calculate the moles associated to nitrogen. But let's make sure, let's track our units and make sure that we have everything we've cross multiplied correctly and our units cancel out, and our answer will be in moles. So we have atmospheres canceling out, we have liters canceling out, we have Kelvin and Kelvin canceling out. In the denominator we have reciprocal moles. So everything is correct as far as the units, in which our answer, our N2, this is actually the answer to this question. Our first part, part A, is 0.7809 moles of nitrogen. Okay, now we're going to go ahead, go back to our stoichiometric problem and put in our value. So we're going to come back over here. And let's go ahead and clean things up a bit. We've got our, okay, it's not working. We've got our moles, so let's go ahead and give ourselves some room here. And we can go ahead and apply that. So we're going to come back over here, and moles, we determine in part A, equals, what we just calculated, equals 0.7809 moles. 0.7809 moles, and then we're going to go ahead and identify, okay, how many moles of the ammonium nitrate would be required to generate that number of moles. And we see here in the balanced chemical sentence, we have a 1-to-1 ratio between that reactant and the product. So we can go ahead and finish up the moles here of that particular reactant is as well 0.7809 moles. Again, we have a molar ratio of 1-to-1. And then the last part we'll go ahead and we are asked to calculate the gram value of the ammonium nitrate. So grams of ammonium nitrate, the grams of ammonium nitrate equals 0.7089 moles. And we're going to go ahead and, based on the periodic table, determine the molar mass of the ammonium nitrate, and having the 2 nitrogens, 4 hydrogens, and 2 oxygens. Its molar mass equals 64.032 grams per mole. So we're going to have 64.032 grams divided by 1 mole. And how many grams, the final answer, how many grams of ammonium nitrate will we need? It will require 50.0 grams of the ammonium nitrate. And that is our stoichiometric problem involving the gas laws.